right, so welcome everybody to this new episode of the Coffee Breakdown podcast. Today the new guest is Tobias Gergs, who recently got his PhD at Ruhr University Bochum in Germany. And actually, Toby and I are colleagues. And he is also the winner of the GC 2022 award last year. Yeah. And I'm really glad to talk with you. Toby is one of the experts, in my view, of surface science, molecular dynamics, machine learning, and so on. And this will be also the topic of today's conversation. So thank you, Toby, for accepting the invitation, for your time, and so on.
Thanks very much for this super kind introduction and for having me.
Yeah, so we would like, so let's start maybe talking a little bit about you. So how did you get interested into, in general, machine learning or into even plasma research? Because what you do is also related to plasma.
Well, actually, it was vice versa. So in the very beginning, I kind of got interested in a method like molecular dynamics.
Okay.
It's a totally different topic, nothing to do with plasma at all. And just after finishing my master thesis, I got a job offer, like for my PhD time or for becoming a PhD student. And this involved the plasma surface interactions. So this is like the very first time plasma emerged into my life, so to say. And so we developed a concept for a project and we pursued the idea. And then on this, let's say, journey of exploring plasma surface interactions, we just, like the whole team, had the idea to mingle in some machine learning. That was just a trial at the very beginning. So it could be useful, could be nice. And the more we started to, let's say, dive into the topic to learn more, we started to understand that this is actually a huge deal and could be of great value for, let's say, plasma surface interactions and the way we understand them and the way we model them.
Okay. Maybe soon we talk a little bit more about the details. So you already introduced, actually, we already introduced this terminology of molecular dynamics. So actually in this channel, we already talked about plasma surface interaction, but not all the people that study this use molecular dynamics. So can you explain us a little bit what this is?
Oh, of course. So actually, molecular dynamics, it sounds very fancy, the name, I have to admit, but on the idea is fairly simple to understand. Assume that you want to describe a system on the atomic level. So you have a lot of atoms. And usually you don't care about the electrons. So you just consider them as atom balls. And you simply assume these are classical particles. So we do not account for any quantum mechanical effects, typically. And what we simply do is we solve Newton's equation of motion for all the atoms. So to some extent, it's like mimicking, like assuming atoms are just balls that move in time and space. But the big difference between, let's say, billiard balls moving in a table or on a table and atoms are the forces between the atoms. And the molecular dynamics, what you typically do is that you spend quite some time to derive interaction potentials that define how the forces have to be described that are acting on the atoms. But once you have the forces, you simply evolve Newton's equation of motion for the atoms. And by doing this, you can study a variety of different topics, scenarios, applications.
Yeah, that is interesting because, for example, in my models, I used to deal mainly with cross sections. That gives a sort of probability of processes or particle interacting, for example. But I'm not really aware what is the status of interaction potential, for example. Are they available for a large number of materials, for example? I don't know, target and projectiles or different species? What is the status of the field?
Yeah, it really depends on what you're interested in. So overall, there's a lot of researchers that spend quite some resources and time on deriving such potentials, and they did an astonishing work. And there are continuously even more potentials, let's say, proposed. So of course, you can define different functional forms. So to some extent, these are just analytical equations, often fairly complex, with some parameters. And
Okay.
some potential functions are well suited to describe certain materials. Like for instance, one is called embedded atom method, well suited for only for metals. So it will perform very bad for metal oxides, for instance. Then you have other potential functions to describe the metal oxides or silicon nitrides, and furthermore. So overall, there are a lot of potentials and parameterizations available for a lot of systems, but it's always the most important first or zero step to check whether the potential that is available for your system, for your process, is valid. Because typically, when people set up such a potential, they have an application in mind. And they don't just do it because they're generous. They usually set up such a potential in that parameterization to study a system on their own. You have to check whether you can transfer what they did to your task. And this can go well, but it can also be challenging.
So this means that you have some macroscopic parameter that you can compare once you use this potential, or how do you check the validity typically?
That really depends, again, on the application, right?
Okay.
So let's say usually you describe, you can of course also describe fluids or gases, but often it's used to study, let's say, surfaces or solid state systems, so block systems. So what you typically first do is having a look at the lattice constant. So really the fundamental system properties, like the lattice constants, is the energy, so the release energy, for instance, of the system in its profound, or its let's say, energetically most favorable state, really the most favorable state. I mean, you can consider different configurations, crystal structures, and you can compare your prediction with the molecular dynamics simulation with quantum mechanical computation, like density functional theory. And you should get a good agreement on these, let's say, basic properties. And then you can proceed. So for instance, have a look at some dynamic properties, energy barriers, and further.
Okay, that's interesting. Okay, but sorry, I was interested into this part, so I wanted to dive a little bit into that. But so molecular dynamics, as you mentioned, is a type of it's a type of model that you can set up to a physics-based model, right? And you were talking about machine learning as well, right? So what is the difference actually between the two? So physics-based and data-driven type of models.
That's actually a good question. I would say the difference is, it depends on the goal that you have in mind. So what can you do with both models, right? So usually, in particular right now, I would say for a lot of applications, a lot of systems, processes, there are already physics model available, less or more accurate. And often we also have data available from the simulation or from experiments, or we can generate data by either method. And it becomes interesting when you have take into account whether you have a lot of data or limited data, and whether you have a physics model or there's none. So let's say in our case, we have a model available, molecular dynamics, and we can study a certain process. And then we also have some data, some experimental data, for instance. This means we could combine both, so we could complement the physics model to be more accurate. And other thing is, I mean, we didn't talk about this, and we don't have to dive into this, but depending on what you want to study, molecular dynamics are quite computationally demanding. So it can easily take months to perform a certain simulation. So with machine learning, you can drastically accelerate the time that is required to make a prediction for a certain, let's say, property or evolution for a given effect. So you can become more realistic and at the same time increase the performance.
Mhm.
And a pure data-driven model, so when there's no physics model available, means we have no physics model, but with, let's say, quite some data available from, let's say, experiment, for instance.
Mhm.
This would allow us to still get a, let's say, correlation or some idea about the process, some insight that helps us to understand and decide, which of
Mhm.
course is not ideal. Ideally, we would like to understand everything and prove it with a model. But if that's not possible right now, it's great that we can use a data-driven model
Mhm.
to help us, to guide us. That's how I would
Yeah.
say these two go away. Or
Yeah, that's true. That is also something I haven't thought about, but that is true that you could, in principle, derive the physics relations without knowing the model a priori, but simply starting from the data.
yeah.
So sort of not the physics, but in terms like the governing equations somehow. So for example, there is a very simple example, of you can solve Newton's equation of motion to have the trajectory of a ball that you can kick, or you can try many times, right, to try to throw a ball, and the computer, of course, maybe, or even a child, who does who tries to throw the ball, it doesn't know about the Newton's equation of motion. It's just by trials and errors.
Mhm.
And eventually, yes, without knowing that, you can figure out maybe the governing equation as well. I'm thinking about application in for example, for anomalous transport, where maybe we don't have a governing model, but
Mhm.
it could be that using a data-driven approach, you still have accurate results.
Yeah. So of course, it would be great. It's always good from my point of view to combine both worlds.
Mm-hmm.
Like it's really nice, right? In the simulation, you know everything, but you're not in the real world. And in the experiment, well, you usually don't know everything, but you're in the real world. So combining both worlds is really powerful. But of course, if you cannot do, if the simulation simply, a model simply does not exist, I
Mm-hmm.
think it's still great that we can, to some extent, rely on data-driven approaches to improve and get insight.
Yeah, true. Okay. Sometimes also we talk about machine learning, deep learning, and so on, and these are used as synonym. Is it really like that, or is it better to call deep learning what you do?
Yeah, I mean, well, to some extent, it is a synonym
Mm-hmm.
when you do deep learning. So usually machine learning is, let's say, a higher level description for deep learning, artificial neural networks, but also a lot of other different topics. It's like really a top level, um, what's the word? A top level word,
Mm-hmm.
or let's say
Yeah,
nomenclature. You may know what I mean, to
yeah.
describe a lot of different methods. So I think, and I think to some extent, people are sometimes surprised that what they have done for years, maybe, or briefly, is actually machine learning. So, for instance, I know that you in your past did PCA,
Mm-hmm.
so principal component analysis, and this is also considered as machine learning.
Yeah, yeah.
And there are a lot of different, let's say, methods available that pursue different tasks in machine learning, and one of which is called deep learning or artificial neural networks. So these are really two synonyms, but it's just, let's say, let's say
Mm-hmm.
one piece of the whole picture.
Okay, okay. Let's try to give some concrete example because sometimes it seems a lot vague. Yeah, we do machine learning and we get something nice, something fast. And so I would like you to tell us something also based on your experience, on your work, like how can realistically we can use machine learning to derive some more knowledge, some more or some computational advantages in first surface kinetics type of application. So can
Yeah.
you tell us how did you start with your work? What was your first application and how did you tackle the challenges?
Mm. Well, first of all, I have to again stress that this is not like solely my work.
Okay,
I
yeah.
did this in cooperation with, let's say, other people, other scientists, of course. But the way we started was, as I mentioned previously, simply give it a test.
Mhm,
So what we did is we considered a very basic process, let's say a very simple one.
mhm,
So the sputtering of a target, for those that are familiar with it, it just simply means you have an iron hitting a material, the target material, it spawns a collision cascade, and this leads to the emission of particles, material. And this is used in the end to deposit a certain thin film. And we started with simply a sputtering process for metal, which I would consider a fairly simple process. And this allows us to move from the molecular dynamic simulations away towards a more simpler but more resource efficient method. And this then allowed us to set up a data set. So we generated data with this more simple model, a lot of data, because it's more simpler, and hence just a few days were sufficient to actually generate a quite substantial data set. And then we performed this kind of, let's say, case study to study different kind of energies like kinetic impulses, and also different shapes of the ion energy distribution function, like how the ions are sampled from. And the interesting part is then that we performed this kind of case study twice. So once with a high resolution, like a nice statistics, which allowed us to predict like how the particles are moved quite nicely. And once we performed like just less kind of particle arrangements. And this then has a rather noisy statistics. So it's really bad. And the idea was that we want to mimic the accuracy of molecular dynamic simulations without really performing molecular dynamic simulations, because we weren't sure whether it's worth it at this point. And then we used this noisy data set. We used it to perform a most simple machine learning or artificial neural network, which is called multi-layer perceptron. And we used it to make predictions for the particles that are emitted from the surface. And we found that like any energy angular distribution functions of these emitted particles were actually almost congruent with those high statistical reference data. So all of a sudden, we found out that simply using this kind of machine learning model allows us to perform way less surface simulations, but with such a post-processing or complementation, we can gain the same statistical outcome in the end, the same results.
Okay. Yeah, that is interesting. So, but this is an application that, well, first of all, let me ask, because a lot of people may be a bit confused or so on. So when you talk about machine learning model, can you explain us some different type of architectures? So what are we talking about?
I think the one which probably most are familiar with, or at least have seen a picture, is that you have some nodes.
Yeah.
And these are interconnected with lines. And these lines represent, say, connection between the nodes, like an information processing typically by a nonlinear function, and furthermore. I think we don't have to go into the detail. But how it works is that you have in a multi-layer perceptron multiple layers. That's what the name stands for.
Yeah.
And each of these layers contains a certain number of nodes. And then the information is simply processed from the left, where you have your input nodes, to some hidden layers with nodes, to the right, where your output nodes is. And then this is simply a regression model from the input to the output. And information processed by all these small lines and all these individual nodes.
Okay. And this is essentially the type of model that you used for the type of architecture that you used for your model.
Exactly. In the beginning. Of course, you can also do more. We talked about these energy angular distribution. And of course, you can understand these as really as energy angular distribution functions, mathematical functions, or just pure sequence of data. But these, you can also understand it as an image. So on the y-axis, you have, for instance, the angle. On the x-axis, and furthermore. And if you have such an image, you can also say, okay, maybe we want to use an image processing tool, like a machine learning for image processing. And this is where, for instance, convolutional neural networks or convolutional layers come into play. So you define a kernel, and you move this kernel over the image. And then you define multiple kernels, and by doing this, and putting them in a sequence, you can extract features from the image. And what we did is, or what one can do is, for instance, to combine such a convolutional neural network architecture with an autoencoder. And an autoencoder is simply means you have the same input and output. So the network tries to reconstruct itself, like the same information, but you can find a bottleneck. So the information has to be processed or has to go through such a bottleneck. And not all information can bypass this bottleneck. And still the network, this autoencoder, tries to reconstruct the original information, and hence only the most important, the key information, are contained in the very end. And this helps to achieve a generalization.
Yeah, for me, this concept is very familiar because, as you know, having tried some PCA, you know, there is this idea of dimensionality reduction, right?
Yeah.
And then from this sort of reduced space or latent space, then you try to go to the original space, to map back to the original spaces. Sometimes, you know, so in fact, this is probably a more sophisticated idea where you can have more complex model, this variation autoencoder, even non-linearities within your system, if I'm correct.
Yeah, I mean, I think actually it's nice that you mentioned or that we mentioned PCA, because I think it's a good idea to simply start with PCA, and maybe what you get from it is already sufficient. So why use a why set up a complicated artificial neural network when PCA yields sufficient or let's say good enough results? But sometimes PCA is not sufficient for what you want to do. Then, you mentioned it, the non-linearities and the additional degrees of freedom can actually become quite handy and allow for what you're looking for.
Yeah, okay, this is very interesting. I mean, from this work, from that you described, from what I understand, there are two interesting concepts, in my opinion. And just one is that is a concept that is very common in plasma physics, where you want to have, for example, lookup tables for different conditions of parameters. And one challenge is to have a very large lookup tables, right? That can become expensive if you want to interpolate between those. Another one is that you can do a little bit more because you can generalize on data. For example, if you have noisy distribution function, you can get a bit more smooth function. So even obtain information on the tail that is not really possible if you do kind of interpolation between points. So I don't know. So I think this is a little bit more information that we can get, in my opinion. So you tried also for larger a larger set of data, if I'm correct, right? Where you change also stoichiometry in your work and so on. So can you tell us a bit more about that?
Yeah, absolutely. So after moving, or after having this successful experience in this first part, we thought, okay, this is great. Let's move on. Let's try more with this. And we did exactly what you mentioned. So we still only had a look at the sputtering for target. Actually, it was a composite target, like of two metals. And we varied this stoichiometry. The idea was, let's see whether we can introduce an, let's say, basic system state that describes the surface into the model. Still, we had in mind, in the long term, we want to move to a molecular dynamics, which provides us not just the stoichiometry, but a huge list of properties for surface. So is this kind of preliminary or basic system state or helpful? Does it work? That's also a good question. So we moved on to this scenario of having different stoichiometries, but we also moved on with the machine learning architecture. And we actually did exactly what I mentioned earlier. That is, we now consider convolutional neural networks to process the energy angular distributions as an image. And we also use an autoencoder, specifically a variational autoencoder, to, in the first step, have a dimensionality reduction of the information of the sputtered particles. And then in the second step, set up a surrogate model or regression model, which maps the incident ion energies and the stoichiometry of the composite target to the output energy angle distribution functions. And this was quite nice because this showed us, and it worked out quite very nice. So, but aside from this, it was nice because such a different architecture allowed us to significantly reduce the number of internal degrees of freedom. I think in the end, for this very, very final surrogate model, around about 1% or less than a percent was actually trained.
Yeah. Okay. Okay.
Mm.
All right. Yeah. And this is here, and there is also a concept that people, ask themselves, how good is this model to extrapolate, to get data out of, the comfort region, let's say.
Yeah.
So
So commonly you say in machine learning, I think you can read it over and over again, that interpolation is quite nice. You mentioned this
yeah, yeah.
previously. That's what you have in mind. And I think that's what most people do, is to use it for generalization when you have noisy data, and interpolation. And extrapolation is typically discouraged. So people
Yeah.
usually say, don't do this. This doesn't work well. And we were aware of this, but we wanted to test it to see
Okay.
whether
Okay.
this is, I mean, we didn't really think it's wrong, but we wanted to see how bad is bad. So when we set up the different stoichiometries, we consider all of them from 0 to 1. So where we have a pure aluminum target or a pure titanium target, but also all in between or some in between. But we only train with a subsection. And we specifically left some of those cases out. Some for testing after the model has been trained, for interpolation, so between the supporting centers, these were really well, the model performed nice, and some outside of the training data set. And here we see that quite visually intuitive, we can quite clearly see that extrapolation doesn't work. So it was no surprise, but it was just, let's say,
Yeah, just a proof of
affirmation for us
concept.
to not
Exactly.
extrapolate.
Okay, okay. But are there methods that can be used to, let's say, tackle this problem, for example? I don't know. For example, I heard about the active learning, stuff like that, but I'm
Yeah,
not sure.
yeah. I mean, it really depends on the architecture and also on the problem you're studying. So there are actually some models for some scenarios which are possible
Yeah.
to extrapolate to some extent. For instance, when you use machine learning model to predict the time series, this
Okay.
can actually to some extent extrapolate if done properly. But here, what you're referring to is, let's say, the more promising approach is if you're extrapolating, simply get more data.
Yeah, that
So
is not really extrapolation at that point,
yeah, but that's
probably,
the
but
point. Active learning means that you would have, let's say, a cycle of um, of having training your machine learning model with available data
yeah.
and seeing where it performs bad. So where is the model insecure about? And then you generate more data, in particular to support the model so where it needs data. So you not just randomly generate data all over the place, but exactly where it's required. So that's
Okay,
not really
okay.
bypassing extrapolation, but it's a way to tackle it, I'd say.
Okay, okay, interesting. Yeah. And then at some point you mentioned also about this molecular dynamics. And so were you successful to apply this model also to molecular dynamics simulation?
Well, this was, to be honest, now really, frankly, I was skeptical doing it the first time
Okay.
because with this sputtering simulations, we
hmm
got easily huge data sets
hmm
and still with statistical challenging representation of the energy angle distributions.
hmm
But when doing molecular dynamics, suddenly we had still statistically challenging representations of
Okay.
physical processes, but also way less data. So it
Oh,
was not
okay.
clear whether this is still working or
hmm
not. So
Yeah.
this is really what I wanted to check. In addition, we also now, since we apply molecular dynamics, thought we can generalize the wall interactions. So studying the sputtering at the target and the growth at the
Hmm.
substrate. And the idea was now to perform for pure metallic case, such molecular dynamics simulations.
Okay.
Again, choosing a rather simple scenario and setting up the data set,
Hmm.
and then train a model and see whether it works. Again, we also moved on for the machine learning mode, like the architecture. Instead of using an autoencoder and combine it with another regression model, we then actually moved on to what we call the physics separated artificial neural network.
Hmm.
And this is
Okay. Yeah, this is very interesting because you are going in fact to a more complex model, physics-based model, but it seems that also the complexity of your machine learning model should increase. Is it like that or?
um, honestly, I'd say that's not it again, it depends on the application,
Mhm.
but I would say it's rather for us a learning experience. So we
Okay.
started we had no clue in the beginning about machine learning,
Yeah,
and
yeah.
started therefore with basic process, which is really simple, and the basic machine learning model or artificial neural networks. Simply, we were not experienced with this one, so let's not think about the more complex one.
Yes,
And
yes.
while slowly increasing the physical complexity, we also complementary increased the complexity of the machine learning model simply
Yeah.
because we felt more secure, more
Okay.
experienced with what we're doing. And we had new ideas what we can do.
Mhm.
So for us, I think it was honestly just a learning experience, which then showed us new ways to go or to try.
Okay. But then what is the advantage of this new architecture, for example, with respect to the previous one?
Yeah, it's so the basic idea was to subdivide the physics,
Uh-huh.
to separate them. In this case, to separate the damage that is created by the ion bombardment on the atomic level to the relaxation of the damage, so a translation from the damage to, for instance,
Uh-huh.
composition, stress, density, and furthermore. And we can make a cut. And such a cut, for instance, reduces the dimensionality of the parameter space.
Okay.
And it was also an interesting test for us because I mentioned in this former work this basic system state,
Uh-huh.
this stoichiometry. Now we define a surface state that was fairly complex. I can't really recall how many properties were in there, but fairly complex surface state and a description of the defect structure. And the idea was that we establish for one of the physical processes, so the ion bombardment induced damage, one
Uh-huh.
regression model, and for the other physical process, so the translation of the damage to the properties, another regression model.
Okay.
And they hand over a description of the surface state,
Mhm.
and the other one tries to um, express the defect structure as a function of the surface state.
So
So we
these are two
also
networks that are communicating with each other somehow.
exactly, and they
Okay.
are alternating
Mhm.
between defect structure and surface state.
Yes, okay, okay, okay. So in principle, if you have a multi-physics type of problem, you can train different networks that
Mhm.
kind of connects with each other.
Yeah.
But one network kind of encloses information about only one part of the physics. So something like that.
Exactly, that was the main idea.
Mhm.
But also what was nice about this is that, I mean, there were some works that hinted towards the circumstance that both of which,
Yeah.
surface state, defect structure, are sufficient to describe the system,
Mhm.
but we were not clear about this. I mean,
Yes.
how to know whether this is really true? And by handing this information over from one to another
Mhm.
and evolving the whole process in time, and still having agreement between the prediction and the reference data, we could show that actually both of which are allow for a complete system description. And this is really nice because, of course, it's nice to show that you can use this descriptor or these descriptors. It's maybe nice for a guy like me doing simulations. But what's really cool about this is that, and we come back to something we talked about in the very beginning. If you now, for this process, have simulation and experimental data, in the simulation, we know everything. We know the surface state and the defect structure. In the experiment, well, they can actually set up the surface state. So the mass density, the composition, and the stress. These are things they can measure. But the atomic defect structure, the way we define it, this is not accessible in the experiment.
I see. And somehow you hide it within the architecture.
Exactly. And this allows us then, in the final model, to simultaneously train with simulation data and experimental data, in spite of a discrepancy regarding the information accessibility.
I see. Okay. That's interesting. Okay, I would like maybe to conclude because here we are entering like really kind of technical part. So recently you have published a work on the Journal of Physics D of Applied Physics titled Physics Separating Artificial Neural Networks for Predicting Sputtering and Thin Film Deposition of Aluminum Nitride in Argon Nitrogen Discharges on experimental timescales. So it's a very long title, but okay, I would like you to very briefly discuss this work because I've read that. I think it's very interesting, especially if you can bridge, explain how did you manage to bridge, you know, timescales that are very short, typical of molecular dynamics simulation, to experimental timescales, so minutes even.
Yeah. So there was still a shortcoming of this former work is that given the small data set, we could actually not bridge the timescales. And this is why we moved on to even a more challenging system, the reactive sputter deposition, which of course is also more interesting for the application. And think about how can we finally tackle these timescale bridging? And the answer is, I'd say, twofold. And the most important part is actually the data generation. And this is where a new idea actually led to a change of perspective. So what we did is to still use molecular dynamics to generate the data. So we use it actually to study the plasma surface interactions and the diffusion processes. But we do this now in a randomized manner. So we continuously randomize the species that are hitting the surface. They are continuously randomize the ion energies and the temperatures of the diffusion process in one simulation. This means we define a circle, but the whole trajectory we are evolving in time is actually quite meaningless. It makes no sense. But the nice part is that this allows us to populate the parameter space super effectively if we consider each individual impingement as data point.
So essentially, correct me if I'm wrong, or maybe I have a wrong interpretation, your physics-based model is a sequence of impingements from molecular dynamics and some sort of surface reorganization of the atom configuration. Is it like that? And then you randomly select your input parameters or your configuration even of your surface.
Yeah, that's actually we randomize all of which.
Okay.
So we also the input parameters, but we also the initial surface state. So the defects are randomly organized, or randomly chosen to really properly populate the whole parameter space that we consider interesting for, or could be interesting for the application in the end.
Yes.
And then we use the data now that's well spread in the parameter space to set up again a physics separating artificial neural network. But this time we do another kind of separation between the plasma surface interaction and the diffusion.
Okay. The surface diffusion here we are talking about.
Actually, we're talking about bulk diffusion.
Bulk diffusion, okay.
I mean, this is quite interesting that you mentioned this, because what you could do, of course, is to have not just two separations, but you could also now
Yeah.
include a third one with surface diffusion.
Mhm.
But at this point, we just consider plasma surface interaction and bulk diffusion.
Mhm.
And we again train two individual regression models and have them coupled all together to establish such a circle.
Mhm.
And then we pass on the system state description from one to another, and this allows us to evolve in time the system state for ongoing bombardment or impingement of ions and particles, neutrals for different kind of surface orientations.
Yes, yes. So one question that I know it came up from this work is really how do you assign time from this process, right? So this is actually quite common in molecular dynamics, how you bridge these very long time scales actually between one impingement and the other.
Yeah, I mean, it's a matter of perspective, right? I know that from the plasma point of view, this is different than from the, let's
Yeah,
say, surface science or material scientist point of view. For the surface side, you can really see it's just a series of impingements.
yeah. Mhm.
And given for instance, simulation or experiment where you know the flux towards the surface or can estimate it
Mhm.
of the different species, and you know the area, it's the surface area of your molecular dynamics simulation,
Mhm.
you can, of course, assess a certain time that is bypassed from one impingement to the other.
Yes.
This does not necessarily mean we solve the whole time span, but to some extent you could. I mean, this thing is the way we solve the diffusion processes, actually not with molecular dynamics, but Monte Carlo. But I think going into detail
Yeah.
would totally be too much for this
Mhm.
podcast. But the way you could also do is to call this diffusion not just once, but to have it call it like 10 times or furthermore, to really try to resolve all the different steps individually. We just found out that it's not necessary for our application.
Yes, yes. And
Mm.
so this is a very interesting outcome because you can simply by data generation, this randomized way that you described, you can describe, you can associate this to a dynamic problem. And this is something that is quite new to me. So a sort of time evolution of the system
Mm.
that you cannot, of course, perform a molecular dynamics for minutes time scale or something like that, right? But if you know your configuration of the system and sort of your probability of reorganizing in a certain way after an event,
Yeah.
then you can actually evolve your system from one state to another. Okay, this is maybe more accurate than saying time evolution. It's actually evolution from one state to another.
That's true. I just think, so I actually absolutely agree with you. I just think assigning a time to this makes it more comparable to
Yeah, yeah,
people who
to
also run simulations, but more importantly, maybe also to those who
mhm,
do experiments, because all of
yeah.
a sudden you can reach process times of minutes, hours, and this allows then the comparison of, well, your simulation, your predictions with the experiment in not in real time, maybe, but still for realistic process times.
Okay, then one question because I'm quite intrigued by this. So, what do you think are the outcomes for this work? Do you see the applicability also to other systems in plasmas or of this method itself?
Yeah, absolutely, actually. So I think the whole topic, and I think this is not new to anybody, of machine learning in
Mhm.
plasma, but frankly also in all other sciences, I guess, science topics, um, is emerging fast and is growing and growing and growing. And I I'm fairly positive that such a method, such a concept will can easily be transferred and will be transferred to other plasma processes that involve plasma surface interaction,
Mhm.
which actually most of them do. Like for instance, you could consider catalysis
Mhm.
or plasma enhanced chemical vapor deposition.
Mhm.
But
Yeah.
also those processes at atmospheric pressure involve surfaces, and actually those are even more complex. And in these cases, such an approach from my point of view, could be even more promising. But
Yeah. Mhm.
yeah, please.
No. Because you know this is interesting because a lot of times we ask, okay, what can is machine learning really useful, right? So now, of course, I mean this question comes from someone like me doing physics-based model, right? And I see machine learning as a tool, but I want the tool sometimes to give me more information than what I can get normally from my model, right? And so I would like to have your opinion on that. So in the world of plasma physics more generally, so these methods for sure are spreading. So you see also in conferences, many people now start to apply. So do you think machine learning can give an added value? So they can provide more information that cannot be obtained by the physics-based model?
Absolutely, yes, I think they can. I
They can,
just
yeah.
just I just think it's not necessarily simple to achieve this.
Hmm.
So consider our work. We spent years on this, and we
Yeah,
did a
yeah.
series of methods. But just in the very end, we succeeded with bridging the timescales.
Hmm.
And this allowed us to, for instance, assess and study the effect of rare events on the evolution of thin film properties
Yeah,
on the atomic level, with molecular dynamics fidelity.
yeah.
This information, well, you can do such a simulation with molecular dynamics, but you don't know where to look,
Hmm.
simply because you cannot resolve these timescales with MD.
Yes. Hmm.
So this actually allowed us to learn something which we were not aware of. At least we guessed it maybe, but we could not prove it.
Hmm.
So it can give an added value, certainly. I just think that it's not necessarily easy to achieve this, but that's also fine. I think
Hmm.
it's super fine to just start with a generalization of noisy data or with an interpolation, because all of these kind of problems help you to get used to the model and to this idea. And I think this is very beneficial. And in the long term, I think then perspectives and ideas will come naturally that show you where you can apply and how you can apply the method or other methods that are related to gain such added benefit.
Yeah, so yeah, there is a lot of things, the fidelity of the model that you're starting, that you're generating your data, and also the machine learning model that you're using and so on. So it's also difficult to think where do you want to spend most of your time, if you have limited time, do you want to get more familiar with all the different machine learning models that exist? Do you want to expand a bit more on the fidelity of the physics-based model?
Yeah, true.
Recently, I see a lot of application also coming from fusion on plasma control, where you don't have maybe high fidelity model. You start maybe from a lower fidelity model, but validate it with experiment. Then you generate a lot of data and you train machine learning model to have a real-time control, for example. Then this is an application where I think, you can get fast model, I think, from machine learning.
Yeah, absolutely. I mean, in the end, maybe not for controlling, but this is also what we did, right? We started with a
Yeah.
simple model,
Hmm.
which gives us a lot of data. And I think that's, if you are new to this topic, a really nice way to go. That if you want to deal with machine learning, I think it's a good idea to some
Yeah.
extent, at least, um, that you're not at the same time try to already do the highly complex, super time demanding simulations or experimental setups. Maybe start with something simple that gets you a lot of data, and then you can always do some machine learning with this and apply artificial neural networks.
Hmm.
And then maybe in a similar way we did it, gradually move on to more complex methods and more complex applications. And of course, you will hear other people that do very fancy machine learning techniques,
Hmm.
and you will maybe directly want to, let's say, apply them to your system, which is fine. But I still think that just a step-by-step process is really
Yes.
beneficial.
Yeah, I really like it, in fact. But in fact, as you're learning every new technique, you should not start, like from very difficult goal, but start learning step by step. That is the best approach. Yeah, this is true. Okay, that is very interesting. I would like to ask you maybe to conclude, maybe there are also some students watching this podcast and so on are interested to learn a bit more about these topics. So do you have some suggestion or material where they can start about, machine learning or things like that?
Yeah, sure. I mean, that's quite nice. A lot of different programs available that we also used, and that makes it really nice to get started with this topic. Like we used, for instance, like the TensorFlow and Keras environment.
Mhm.
And this is really nice because it's well documented. It's written in Python, so it's fairly simple to get
So
used to.
Python is the programming language to go that you think if you want to do machine learning at this moment.
Well, there are certainly also more, but I think if you are starting with this and you've never done it before, I mean, it's nice because it's not like dealing with two things at once. I mean, if you use a more complex program language, everything becomes more, let's say, encrypted. So it's not that intuitive to
Yeah.
understand your code, maybe. And if you just get started, I think it could be an added obstacle compared to Python, which is, well, nice to read, easy to implement, and gives you quick,
Mhm.
nice results. So I would really recommend those two, but there are way, way more, like which are suitable, and they are not worse, not necessarily better, but I mean, there are lots to choose from. But it's what I think is really nice for these kind of codes, but also others, that you have a really active community.
Mhm.
So when you have questions or you're uncertain about something, really Google is your friend, and you can find so many nice solutions. And typically somebody else encountered a similar problem, and
Mhm.
you can learn from this. And I think this really gives you a nice kickstart. But of course, there are also, yeah, sorry, please
No,
go
no,
ahead.
no. Please continue. Yeah.
I mean, there are also a series of books that are available that you
Mhm.
can have a look at. And like, for instance, I have found one that I would like to highlight
Mhm.
from Aurelio Geron. I hope I spelled
Okay.
his name
We can
correctly.
put the link in the description anyway. So yeah.
That's perfect. Actually, let's do it like this. That's maybe more convenient.
Mhm.
And
Maybe you
yes,
can say the title. What is the title of the book?
the title of the book is Hands-on Machine Learning with
Okay.
Scikit-learn, Keras, and TensorFlow,
Mhm.
concepts, tools, and techniques to build intelligent systems.
Okay. Okay. And also, I like really much your approach, sort of bottom up, if you want to call it like that, because I have a lot of friends also interested you know, try some stuff with machine learning and so on. But they have the idea, yeah, but I need a very powerful computer. I need, to have a large storage system because I need a lot of data to do interesting stuff, and I don't have a GPU, for example. So
Mm.
can you what do you recommend for that? Do I really need a really large setup, very expensive, or can I try to learn the basics even from my laptop?
Absolutely from laptop. Actually, I'd say the majority, so maybe around about 75% of the machine learning work that we just discussed was done with a laptop.
Mhm.
So in the very end, we moved on to a class, like to a server with GPU. But for the most of those cases, we simply use the CPU in a laptop.
Okay. Okay.
So that's actually can be done quite nicely, I'd say.
Okay, so I think it's very interesting because for me, I see it as new type of approaches to try to tackle problems. There are many problems in plasma physics, plasma chemistry, plasma surface interaction, and I think new methods are very welcome in this community. And I would like to thank you, Toby, for this nice explanation of the different parts, very, challenging, very detailed. And with this, I also want to say goodbye to you and also to all the audience Okay, and see you soon.
Bye bye.